Okay, well here we are. It's only 7:59, so we'll wait a couple of minutes for people to come in. But so this is very strange how this worked out. If you've ever driven on 684, they have signs all over the place that are trying to give you warning messages, and all day long Monday and Tuesday they kept flashing messages saying Tuesday night, stay off the roads. It's going to snow like crazy. Just stay home, that kind of thing. And usually when they do that, it turns out that they're right. I think what ended up happening was that it snowed in the city, but not up here. So this wasn't absolutely necessary. But on the other hand, I've been coughing and sneezing all morning, so it's probably just as well that we're doing this online. So, normally in any semester, there's always 1 or 2 days where the weather is very dicey, or else, I'm not feeling the best. So, it's not unusual to have 1 or 2 Zoom sessions, at least in the spring semester. So, it has some good advantages, doing it this way, because now this way you don't have to come outside in the brutal cold. You don't have to drive to school if you're a commuter. And if necessary, there'll be a recording of this that you can watch later on. And so now it sometimes, I mean, I probably could put it into Brightspace too, but the problem with these videos is that they take up a lot of space. So what I will be doing, maybe I'll put it there, but for sure I'll be putting it in my YouTube account, which I do have because over the years I've made quite a few recordings for different classes. So if you go there, I think all you need to know to find my account is DOCTORACA. That should take care of it. I don't know if typing my name will do the trick. There might be other Alan Andersons out there. This is it though. And so when you get there, you'll see there's a lot of videos, but they're all teaching videos. There's no music or anything in there. So, but the key thing here is that because I've got so many videos, I've set up what's called a playlist. I'm sure you're familiar with this idea. And there isn't one there now because you have to wait till the first video is ready. But when the class is over, I'll be creating a playlist for this class, and it'll have a title, something simple like Math 1060 Spring 2025 or something like that. And then the video will get stored there if you want to watch it. Now, of course, if you're here now, there's really no need. You don't have to watch it. There's no point. But for anyone who, let's say, didn't find out about this or who's late or whatever, it'll be there. So there'll be a permanent recording of it. And I don't think these ever there's no due date. There's no expiration dates in any of these that I'm aware of. So, you can watch these throughout the rest of the semester. And while you're here, if you want, you can look at some of my other stuff. Like if you want to learn more about calculus, I've got it here. I've got a lot of stuff here. And it's all public, by the way. I made sure it's all public so anybody can look at these. You don't need a password, let's say. What's interesting is sometimes I find that people are watching these who are not part of my class, and that surprises me a little bit. So, and then every so often I get emails from YouTube saying, you're not taking full advantage of your capabilities of monetizing your content or something like that. I guess they think I'm doing this for the money. And, but anyway, so here's where you'll find it. So getting back to the material, what we need to do here is start working on the problem sets for the first 2 chapters. Just a quick reminder, chapter 5 and 6 are the content of the first midterm. And so we're very nearly close to being done with chapter 6. 8 is next. And when we start 8, you'll see that it's a very different subject than what we're doing here. And so we're going to have 3 problem sets for chapter 5 and 1 for chapter 6. And when those are done, there's also what we call a sample midterm, which essentially ties it all together. And if you go look in your account, where is it? All right, here we go. Let me just open it up real fast. You'll see that it's already in there. I posted it at the beginning of the semester. Okay, hold on. So yes, if you go look ahead. Now the problem sets for the chapters are in the same folders as the chapter notes. Here we are. If you're wondering where they are. So for example, the chapter 5 problems that we're about to look at are here. And so all the notes are here, all the problems are, oh, and the video links. If you notice, there typically are 2 copies of each because all these were produced in a PC. And in some cases, I needed to use this specialized equation editor. The problem with that is that if you open these same files on a Mac, there's always a risk that it may not look the same, especially when there's graphs involved or equations or symbols. The 2 platforms are not always perfectly compatible with those types of things. So the PDFs are here in case that happens. The PDFs are essentially photographs of the documents that are produced. So if you open up a PowerPoint, let's say, and there's a bunch of blanks in there or weird symbols, then you can just go ahead and look at the PDF. If you're using a PC, this shouldn't be a problem, but if you're using a Mac, you might run into this from time to time. So just as a precaution, I've got 2 copies of everything. And if you want to watch our videos again, here they are. These are taken from YouTube. I didn't make them, so they don't belong to me. And so today we'll be doing the first 2 of these. Next week, we'll be doing the third chapter 5 problem. And in fact, I think I wrote it out a schedule a couple of weeks ago. Let me just confirm real fast what we're going to do the next few weeks, because we don't want to wait forever to take the first midterm, because we do have to keep an eye on the calendar. After all, there's going to be a spring break sometime in March, and we'd like to get it out of the way before then. So I know one week I did write this down. Hold on a second. Just to clarify. Here we go. So today's the 12th. I see. All right. So let me just write this down somewhere. And I'll remind everybody too. So here's what the schedule that I want for the next few weeks. So today's the 12th. Chapter 5 problem sets numbers 1 and 2. And the following Wednesday would be, I think what we should do is the third and final chapter 5 problem set. But just to make sure we don't run out of time, I'd also like to do the chapter 6 problem set. Now that might take up the entire class, by the way, because the chapter 6 problem set is quite long and intensive. So we'll see how that goes. And then that means that on the 26th, we can do the sample midterm. Oops. And again, the sample midterm is essentially more practice. It covers the 2 chapters all mixed together. And you'll find that in Brightspace in a different folder. It's way down here. Oh, wait a minute. Hold on. Maybe not. Oh, I'm in the wrong one. Sorry. I was going to say what happened here. Here it is. Yeah, there it is. Oh, I knew it. Yeah, here it is. Way at the bottom, sample midterm number 1. And you'll see, and also what's included in this folder is the formula sheet that you'll actually have in the test. So in other words, there are some formulas you will not need to memorize, and they're on this formula sheet. Now we haven't really gotten to all of these yet. Well, actually, maybe, yeah, I guess we have. But anyway, so these are the ones you don't have to worry about memorizing. Any other formulas that are missing from this formula sheet, of course, you do need to know them. But at least this way you know what to expect when you walk into that test. All right. So then with all that being said, that means on the 5th, then we'll do the actual midterm. Chapters 5 and 6 only. And then that's all we're going to do that day. In other words, because it's hard to predict how long it's going to take. Some people can knock it off in an hour and a half or 2 hours. Some people need the whole full 4 hours, whatever we have. So it's been my experience that the best thing to do is to simply have nothing else scheduled on that day but the midterms. Okay, so this is where we're going, including today, for the next 4 sessions. And so I will, of course, remind you about this as we go along. I don't remember when the spring break is. It's probably about 2 weeks after this, maybe 3. And then in the meantime, if there's any extra time available, we'll carry on with the new content, which means chapter 8, and then eventually we'll get to the last 2 chapters, which are 11 and 12. So anyway, that's where we're going. So why don't we go to the chapter 5 problem set. Now, by the way, all the solutions that I'm about to write onto this document, I will be posting them on Brightspace when we're done. Okay, so in other words, I actually have in front of me this tablet, a very good tablet, as a matter of fact, that lets me write on the screen. So it's as if I were writing on the whiteboard. And so you'll see that as we go along, I'll be writing in all the solutions, and then I'll save them and post them to Brightspace so you have a copy. Okay. All right. So with all that being said, let's do this. Now, you recognize this content from way, way back in the beginning of the course. Remember what factors are. These are integers whose product equal this number. Actually, they're not even integers, they're the natural numbers. We don't include 0, we don't have negatives, we don't have any fractions. The factors imply that they're positive integers. So if you were to write down all of the pairs of integers, not integers, sorry, natural numbers, whose product is 16, you would have 1 times 16, 2 times 8, 4 times 4, and that's it. You don't need to separately write 8 times 2 because it's already there. So you can leave it like this if you want on the test, but you might want to write it out in a list like this. And by convention, of course, we'll write them from the smallest to the largest. And that's all you have to do. Okay. Now, if the question asks you on the test whether this is a prime number or not, just as a quick reminder, prime number only has 2 factors. One and itself. Okay, for every other case, we have a composite number, which means it has more factors in addition to one and itself. I mean, you could express this in a lot of different ways, but clearly 16 is a composite number. So all the natural numbers fall into one of these 2 categories except one itself. One is an exceptional case, one is neither prime or a composite. It seems strange, but that's what ended up happening. And 0 is not part of this because we're only including the natural numbers. And if you remember from day 1, the natural numbers are 1, 2, 3, 4, et cetera, et cetera. Okay, so I just thought I'd throw that in there just in case we need that. Now here's 225. And by the way, with these factoring questions, the biggest risk really is that you overlook something. So your strategy should probably be to try all the natural numbers, let's say from 1 to 10, and see if any of them make sense. So for example, here, clearly 2 is not a factor because this is not an even number. How about 3 though? Well, there's a quick and easy way to see if 3 is a factor. I think I mentioned this in class. Well, you can go to your calculator, of course. I mean, that option is always on the table. But here's an interesting strategy. If the sum of the digits is a multiple of 3, then 3 is a factor. So in this case, if you take your 225 and you add up the digits, well, there you go. There's your 9. 9 is a multiple of 3. That implies that 3 is a factor of 225. So that means that when you divide 3 into 225, the result will be a natural number. So I'll tell you what. Now, I'll have to start all over again with this list. 225 equals 1 times 225. So 3, turns out that that's 3 times 75. Now 4 clearly doesn't work because it's an even number. 5 does work because this number ends with a 5. Okay, so in other words, it's 5 times 45. How about 6? No, six doesn't often divide evenly into it's often not the case, let's say, that 6 is a factor. 7 is also not that commonly a factor, but 8 can't be right because 8, of course, is an even number. How about 9? Well, we just got through seeing that 3 divides evenly into 225. It's possible that 9 does as well, and yes, it does. All right, well, how about 10? 11? No, I don't think so. 12, 13. Ah, wait a minute. 225 is a perfect square. It equals 15 squared. So, wow, that's a lot of factors. So we end up with 3, 5, 9, 15. Oh, what did I do here? This should have been 25. Sorry. That's it. There's a lot of them. Some of these, even surprisingly, I mean, even a number that's relatively small, like 225, has a lot of factors. So you never know from one number to the next. Some of them have a lot of factors, and some of them have hardly any. Okay. So there's how we find the factors of 225. Then we have 126. Well, we know right away that 2 is a factor. Three. Now, again, if you add these digits up, oh yeah, there you go. Therefore, 3 must evenly divide into here. And in fact, it's 3 times 42. Not 4, not 5, clearly. How about 6? Well, what do you know? This time 6 is a factor. Now, how about 7? Now, by the way, there are rules, for finding factors. Like, we know how to determine if a number has a factor of 3, for 5, we know that one. We know how to do it for 10. It turns out that there are rules for every case from 1 to 10, but some of them are just so complicated that you probably should just use your calculator. Okay. In other words, instead of trying to remember a rule, why don't you just take out your calculator? 126 divided by 7. There you go. It's 18. It's not obvious at all. How about 8? Let's try that. No. How about 9? No. Yes, look at that. It's 9 times 14. Jeez, wow, it just goes, the list goes on and on and on. Now, how about not 10? 11, no. 12, no. 13, no. And then, now we can stop because we already have 14. So that's it, we're done. So let's write up the list. Yeah, so you can see this is a pretty small number, and yet look, all these factors. There's probably a a theorem floating around somewhere which sets a limit on how many factors a number can have, but we're not going to get into that right now. And then for 54, let's see what we've got. So you can see 5 plus 4 is 9. It's divisible by 3, 18. Okay. Not 4, not 5. 6. Oh, yeah. And then, yeah, that's it. We're done. Because 7 is not a factor, 8 is not a factor. We already have a 9. So we have this. The factors are all right. So all of these, by the way, are composite numbers, as you can see. If you had instead something like 17, it would just be 1 and 17, which means that it's prime. Okay, so that's what it means to be. All right, what else do we have to multiples? Now, multiples are easy. All right. Literally, all you're doing is multiplying the number by the first 5 natural numbers, 1 through 5. So, for example, 3 has factors 3, 6, 9, 12, 15. Okay. 7 would be 7, 14, 21, 28, 35. Okay. Oh boy, this one is pretty easy. For 12, we have 12, 24, 36, 48, 60. And then finally, we have 15, 30, 45, 60, and 75. So these are very straightforward. All right, let me just make this a little prettier. Okay, prime factors. Now, this is the one that where we use the trees, remember? So just a quick reminder, can be determined with a binomial tree. Recall that one is not a number. So that should guide you as you draw your tree. So in other words, don't write one in there because it's a factor, it's not a prime factor. Here, we're only interested in prime factors. So also remember that no matter how you go through this tree, you're going to get the same answer regardless of which direction you go. So for example, here, we can break it up into 2 times 8. Now 8 is not prime, so therefore we carry on. And again, 4 is not prime, so we keep going. And only when all of these numbers are prime do we stop. So therefore, we can say that the prime factorization of 16 is either 2 times itself 4 times, or if you want, you can write it as 2 to the 4th power. Okay, that's how this is done. How about 18? Now 18, you can see is a multiple of 3. So we're going to get something a little different here. What do you know? That was easy. So this product you're seeing here is called the prime factorization of 18. So 2, 3, and 3 are the prime factors, but when you multiply them out, it becomes the prime factorization. All right, the prime factors of 1296. Now, clearly 2 is in there somewhere. Okay, well, that one is kind of a mess. Let's see if I can move this whole thing. Ooh, sometimes I get lucky. I'm still learning how to use this tablet, by the way. Sometimes I can move the entire object and sometimes I can't. I don't know what the logic is here, but there it is. If you're studying graphic art or something, I'm sure you use tablets all the time for your work, which, by the way, you probably noticed. Look at me. I have Lightroom and I have Photoshop down here. So I do dabble in this stuff too. Okay. So anyway, now 81. So we can write this in a few different ways. For example, 9 times 9. Okay, and that leaves us now look at all those factors. 1, 2, 3, 4. We have 4 twos and then 4 threes. Or else, if you want to be more compact, you can write it like this. That's wow, that was a lot of prime factors. But now 1960 might have even more because it's such a large number and it's even. So I usually start with 2 or 3. I find that it's easier that way. But now you can see it's pretty clear that 7 is going to get involved somehow. Okay. So, and again, if you went in a slightly different direction, if you wrote up here, for example, 2 times 245, you still would have gotten the same answer by the time you were finished. So it's like taking a different path to the same target. So it actually doesn't have more, it's got different factors, but not more factors. So again, you can't really tell just by looking at a number. Now, this is interesting. This number is 17. Now, 17 is a prime number. The factors are 1 and 17. But guess what? Neither one of those is a prime number. So what do we do now? I'm sorry. What did I say? No, 1 is not prime, 17 is. So in other words, in a case like this, um, we say that 17 has one prime factor only, which is 17 itself. Okay, don't count the 1. It is not prime, but 17 is. So therefore, when you have a prime number like this, it's going to have exactly one prime factor, and that's the number itself. Okay. Now, we can apply this to these greatest common factor problems in the following way. So if you remember, what we were doing here was to find greatest common factor of 2 numbers. Find the prime factorization, both numbers, using the tree probably, although that's not the only way you can do it. And then the product of the common prime factors is the greatest common factor. So that sounds very complicated, but we've already seen this actually is very straightforward. I just want to quickly remind you what we're about to do. So we've got 3 and 1 for 3. So this first one is quite simple. So this is the only prime factor for 3. So what do they have in common? Okay, they have 1 3 in common. 3 has a prime factor of 3. 9 has 2 3s, but between the two of them, what they have in common is 3. So that implies that 3 is the greatest common factor of 3 and 9. Okay, so we're only interested in what they have in common. If anything, you'll see that there might be cases where they don't have anything in common. Let's try these two. So they only have one number in common, that's the 5. And so therefore, 5 is what we're looking for. That's the largest natural number that evenly divides into both 10 and 35. Okay. How about 7 and 10? Now, this is a strange case. This one has a prime factor of 7. This one has 2 and 5. Guess what? They have nothing in common. All right, or at least no prime factors. So since 7 and 10 have no common factors, by definition, we say that the greatest common factor is 1. Oops, what happened there? Okay, so when you see something like that, we have two numbers that do not have any primes in common. We just conclude that the greatest common factor is 1. Okay, so when you have an oddball case like this, you just say that the correct answer is 1. So in math, a lot of times when we have oddball results like this, there is some uh, conclusion that we are meant to draw from this. And here we would just say, oh, then therefore it must be 1. And here you can see the same thing is about to happen because we have 6, which is 2 and 3, and 11, which is 1 and 11. They have no common factors. At least, I'm sorry, they have no common prime factors. Actually, I just realized I typed this incorrectly up here. This should have said prime factors. Okay. And the same thing is happening here since 6 and 10, 11 rather, have no common prime factors. Their greatest common factor is 1. End of story. All right. Very good. Now, least common multiples are quite straightforward because, well, there might be more sophisticated ways of doing this. But I think your best bet is to simply write them out. So in other words, the multiples of 5 are 5, 10, 15, 20, 25, 30, et cetera, et cetera. You can stop it. The thing is, it's hard to know when to stop if you don't have enough. You'll see right away. Say, wait a minute, let me keep going. And at some point you'll say, wait a minute, let's look at the 2. And here we go. They both have a 50. There's no common multiple smaller than 50. Oh, wait, yes, there is. I'm sorry. I just realized it's 30, not 50. Oops, it is 30 because I wasn't looking carefully enough. No, I'm sorry, it's not. It's 10 itself. I just realized okay, no, it's 10. Yeah, I was looking in the wrong direction, that's for sure. Yes, it is 10 because they both have that as a common multiple. There are several common multiples, but the smallest one, which is what we're after, is the 10. The 50 certainly is a common multiple, not the one we're looking for. All right. Now we can do the same thing with 12 and 24. Now, here we can kind of stop. I, I'll write a few more, but it's pretty clear before we go any further that it's going to be 24. So in some of these cases, the least common multiple is the larger of the two numbers. And that actually has happened twice in a row now. Sometimes the least common multiple is the product of the two numbers. So in other words, if you're desperately searching for a common multiple and you can't seem to find it, try the product of the two numbers. That might be your answer. Like here, for example, we have 5. And 7. And you notice this time it is the product of the two, 35. So we know for sure that will be a common multiple. It may not be the least, but it definitely will be a common multiple. So here, all right. And then finally we have 6 and 10. And then we have so if you look carefully at those two lists, you'll see that the smallest one they have in common is 30. All right, now word problems. Now, whenever I mention word problems, I hear a lot of growling in the class. I'm not sure why people dislike word problems so much, but the thing about word problems is that it's essentially the same concepts, but with English instead of math. I mean, really, that's all it is. So, what your job here is to figure out what kind of problem is this. Now, up to this point, we've really only done a handful of concepts. So it might be that we have to find common factors of some kind, maybe prime numbers, least common multiples, greatest common factors. So let's take a look at it for a second. We have two people riding their bicycles on a circular trail. They start together, but one of them is faster than the other. Okay, now that's a terrible circle. You know what I just realized since writing in Word, um, I can get a perfect circle. That looks like an oval. Well, that's kind of nice. I can make it as big as I want. All right, so let's just say we have the two people. Oh, let's say it's John and Bill. And they get together and say, "Hey, let's go bicycle riding," but they don't agree to ride at the same speed. All right, they don't have to be next to each other the whole time. It's not like they're walking someplace in the city or something, and they mean to have a conversation with each other. They're just riding. Okay, they're just getting exercise. So they carry on, and one of them is faster than the other. Okay, so let's say John is the faster of the two. He can get around the whole thing in 24 minutes. Bill takes 36 minutes. He's not in quite the same shape as John, let's say. Now, here's the thing. As soon as they start bicycling, John is going to be getting ahead of Bill. But because it's a circle, eventually they'll meet up again at the starting point. The question is when. Okay, so there's going to come a time, and let's say they've agreed that when that happens, they'll go to lunch. All right. The question is, how long is this going to take? So if you look at John, John will return to the starting in 24 minutes. But guess what? He can go around again and he'll be back in 48 minutes. And then again, 72 minutes. He's really, really in really good shape. You know, he can go on and on and on. Whereas Bill, 36 minutes, he'll be there, but John won't. He'll already have gone past him. So all of a sudden you realize, guess what? In 72 minutes, they'll catch up with each other. So basically, what we've just done is solve for the least common multiple of both of them. So John and Bill will return to the starting point in 72 minutes. So in other words, all of this was just another way of saying what is the least common multiple of 24 and 36. So if I asked you that in the first place, you would have said, oh, no problem. I know exactly how to do that. It's a breeze. But because there's words involved, it becomes more mysterious. Once you recognize that it's nothing but a least common multiple problem, you're all set. So your strategy for these scary looking word problems is to basically say, well, what kind of problem is this? Have I seen this before? Have I done this with algebra? And once you catch on to that, you're all set. Huh? See that? Wow. Okay. So now 24 is a fun question. What's happening here is we have lighthouses. Now, lighthouses at this point in time are really not being used for the original purpose. I mean, the point of a lighthouse was to make it easier for ships to see where they were going at night. We've had lighthouses for quite a long time. In fact, George Washington actually signed a bill at one point authorizing the building of lighthouses along the East Coast because it's especially dangerous, like areas around Cape Cod, for example. In fact, the area, if you're not familiar with Cape Cod, the areas off of Truro um, are sometimes called the graveyard of the Atlantic. Well, you kind of figure out why. There's a very famous pirate ship that crashed there, the Wyandotte, in 1717. Just as a fun side note, and there's actually a museum there now. What happened was everybody knew that this ship had crashed, and it was a pirate ship loaded with treasure. And they ran into a storm, and they never made it. And so there's a very well-known treasure hunter named Barry Clifford, and he decided that, you know what, let's go find the Wyandotte. And oh, it took a long time, a lot of years and a lot of money were spent, but he did eventually find it. And was able to recover quite a bit of pirate treasure, by the way. But here's the thing, though. They also recovered a lot of like the cannons and a lot of the pirate equipment and, you know, weapons and just normal things like teacups and stuff like that. And so there's actually a museum in Yarmouth. I think they call it the Pirate Museum or possibly the Wyandotte Museum. But if you want to see all these pirate artifacts, that's where you can go. And none of this would have been possible if there hadn't been for that storm in 1717. So anyway, so these lighthouses are sitting on the shore, and the pattern of flashing is what lets the ships know which one they're looking at and where they are. So let's say these have been set up so that the first lighthouse flashes every 10 seconds. Now, also, they probably use different colors as well, but this way the ships coming along are well aware that this particular lighthouse at this location flashes every 10 seconds. And lighthouse 2 is every 15 seconds. So I think you can see where this is going. Lighthouse 3 is every 20 seconds. And lighthouse 4 is every 30 seconds. So they start together at the same time, and then when will they all flash again at the same time is the question. So it's the same exact setup. It's a least common multiple problem. And guess what? That happens to be 60. So in other words, now, and by the way, this is an interesting result because up to this point, every time we had least common multiples, it was only two numbers. But this shows us that we can have any number we want. We can have a least common multiple for 3 or 4 or 5 numbers. There's no limit. So the lighthouses will all flash again in 60 seconds. This is the least common multiple of all 4 lighthouses. Okay, so that's how this was done. Okay, so okay, that's part one. I think probably you did very well with this one. There's nothing terribly difficult in this problem set, except maybe interpreting the word problems. So, like I said, I'm going to post this on Brightspace later on, and now we're going to move on to part 2 before we start something new. Oh, now you can see this one is a little bit messier. Okay, this one is where we're looking at radicals. No, this isn't too bad. Okay. So, it's funny how didn't realize this was possible. I guess somebody else has a tablet. And so somehow or other, I'm able to see what you're doing there. I don't know how. I don't understand the technology. So maybe next time we meet in person, you can tell me how that's done. But anyway, so let's carry on with this one. See, it's a Wacom, by the way. These are really good. They're very well built. They're used by professional graphic designers for their art. So that's why I said you're probably familiar with what I'm doing here. If you're in that area, I mean. All right. So is radical 49 rational or irrational? Well, this is one of those cases where 49 is a perfect square. Although it doesn't ask us for this, but which means that square root is an integer. And of course, integers are rational. Therefore, square root of 49 is a rational number. Okay, that's all you need to know. When it comes to square roots, remember the rule. Square root of a perfect square is rational. The square root of any other number is irrational. So there's only 2 cases you have to worry about. So that being the case, if you look at number 2, it's very easy because clearly 37 is not a perfect square. Since 37 is not a perfect square, the square root 37 is irrational. That's all you need to know. Okay. Now, this one is a little bit tricky because remember, we discussed this. When you're looking at, oh boy, you know what I just realized? You see this Copilot thing? They've been working on this for a while, Microsoft. It is their AI tool, basically. And in small stages, they're making it more and more aggressive about offering you help as you go along. And I don't have the slightest idea how it works. So I'm going to try to learn some of it. But Um, like here's a perfect example. It thinks I'm not sure what I want to do. I want to see just out of curiosity what it does. So we're all okay. I don't whatever happened here. Oh, now you see what it did. I thought it was going to draw a picture of the square root of two, but instead it thinks I wanted to know if the square root of two is irrational. Wow, that was pretty clever of it. I'm kind of impressed. I mean, if that was what I wanted to know, I'd be all set right now. Um, but how did it get that out of draw the square root of two? It must have read the previous line. Boy, this is interesting. I'm going to keep it, but we no, I'll get rid of it. We don't need it right now. But boy, that's kind of scary. Well, yes and no. It's good and it's bad. It's good because if I'm desperate, I can see what it says about this. But on the other hand, it's trying to do all my thinking for me, which is not cool. So I'll just get that out of there. And so, but it did raise an important point that the way we tell if a number is rational or irrational is a rational number with a decimal. Now, by the way, if a number is an integer, let's take a step back. An integer is by definition rational. All the integers are rational. Right, end of story, because you can always rewrite it as itself over one, no problem there. But all other numbers can be identified as either rational or irrational by looking at the decimal digits after the decimal. If the digits are repeating, which means there's a pattern, a repeated pattern, or if they terminate, and which means they end eventually. Now, terminate simply means there are a finite number of digits after the decimal point. Then the number is rational. Otherwise, it is irrational. Okay. So in this one, now the reason why this one is tricky is because if you notice, when you first look at it, if you're not careful, you'll see it may look like there's a pattern, but there isn't, because it goes from 2, 3 to 3, 3 to 3, 3, 3. So the number of threes keeps changing. So here, there is no pattern. And the dots indicate that it doesn't terminate either, by the way. No pattern. And the number of decimals or digits after the decimal point is infinite. Therefore, the number is irrational. Okay. Now, on the other hand, just as a counterexample, a number like this, 2, 3, 2, 3, 2, 3, 2, 3, is rational because there is a pattern. Okay, so just so you can see the difference between the two. Okay, so this one is 2, 3, it never changes. And also don't forget, with something like this, we can rewrite it as that bar means that those are the digits that are being repeated forever. Okay. Nice. Okay, so now you know how to do this. 5, 6 is clearly rational because it is a ratio of two integers. Now, you don't necessarily have to explain why. I mean, it's just saying, is it rational or not, or irrational? But whenever possible, you might want to think about why this is your answer, because it'll help you understand what you're doing. Now, we know that pi is irrational. We don't have to prove it. Pi, but I mean, if you wanted to, you could take a look at all those digits and you would see that there's no pattern and it never stops. It's infinite. There is no pattern to the digits after the decimal, and it is not terminating. If you go to the internet, you'll see that you can find the pi expressed in any number of digits that you want. Mathematicians are constantly working on stuff like this. Just because they enjoy it, but also, they want to write research papers and stuff. And, something about pi. Wait a minute. What just happened here? All right. I almost accidentally showed you one of my own videos. Oh, I almost ended the meeting too. Here we go. This is where AI would probably be very helpful. Even if there isn't a website that actually has this, AI is like, oh, sure, no problem. Let me show you the first 100 digits of pi. Okay. Now, you know that when you go to search engines these days, they often try to show you AI stuff first, especially Google. And then if you're determined enough, you can find an actual website. Okay, so now look at those digits. There are no repeating patterns, and it does go on forever. Okay. Now, if you're really serious about math, yes, March 14th is Pi Day because those are the first three digits. And in the year 2015, everyone got all excited because it was 3/14/15. Maybe you don't remember that. That was a while ago. And um, so, this is when I guess AI could really come in handy. Like you could say, who first discovered pi? It doesn't have any opinion about that, but it does show us this article. If you're really interested, you can find the history of just about any mathematical concept. All right, anyway. So here we go. Now, zero by definition is rational because now, again, that's all you had to do here, but I just want you to see why. 0/1, 0 can be written as 0/1, and 0 and 1 are both integers. Therefore, 0 is rational. Okay. So in other words, there's a reason behind it. It's not, you can memorize it if you want. The question doesn't ask why, that's fine. But it's nice to know why. Okay. Oh, simplifications. Oh my God. No, this is not hard at all. So just in a nutshell, our goal is to rewrite the number under the square root sign as a product of two numbers if one of these is the perfect square, then the radical used. Okay. So here, for example, if you think about the factors of 24, say, here we go. We'll choose these two because 4 is a perfect square. Watch what happens. Oh yeah, there it is. So now if you'd chosen 3 times 8, you would have gotten nowhere. You would have had a result that is no simpler than radical 24. So now radical 24 and 2 radical 6 mean the same thing. Mathematically, they're the same thing, but normally in math, as you know, we prefer everything to be as simple as possible. So we always try to keep the radicals as small as possible. We reduce them whenever there's an opportunity to do so. Just like fractions, we always reduce them as much as possible. Okay. Or, there's other situations where we always try to simplify as much as possible. All right, what about this one? Aha, well, look what we can do. Okay, so now we're rolling. And by the way, just like with prime factorization, there can be multiple ways of getting to the same point. Okay, so in other words, like this is an example of what I mean. 80. If you wrote a list, all the factors of 80, it's a long list. You would say, ooh, look at this, 4 radical 10. Or we could break it up into 4 times 10. Wait, sorry, 4 times 20. What am I saying? But if you keep going, um, eventually you realize there's 2 ways of writing this with a perfect square. And usually if there's an option like that, you should choose the larger of the two because you'll see that it's going to be a little quicker. So for example, here, if you had chosen 4 times 20, you still would have gotten to the same point, but you would have needed more steps. Okay, so let's write it like this. 4 times 20. But then you would have realized, wait a minute, look what we can do. Yeah, there you go. So in other words, in this case, there were at least 2 equivalent ways of doing this. One is a little quicker than the other, but they're both going to get us the same answer. Okay, and that's of course the big deal. I mean, we have to have the right answer, but with such a large number like 80, there might be multiple ways of getting to the same point. How about this one? Now, it may not be obvious. This one, by the way, is not divisible by 3 because 1 plus 7 plus 5 adds up to 13, not divisible by 3. Okay. So how about not 2, not 3, not 4, obviously. How about 5? Wait a minute. It's going to be wait, 5 into 175 is 20 35. Okay, that's what I thought. All right. Um, wow, what else do we have here? Let's try this. Oh, wait, hold on. There we go. I went right past it. It's 7. Now we're talking. Okay, great. So we know we can stop right here because clearly 25 is a perfect square. And that's it. It's not going to get any simpler than that because 7 is a prime number. And by the way, that's how you know here that you're not done because this is not a prime number right here. Okay. All right. How about 30? Now, this is a very odd case. Look at the factors of 30. Guess what? None of these are prime numbers. Sorry, perfect squares. So that means radical 30 can't be simplified. Now, it can be rewritten, but it wouldn't be any simpler than what you have here. So in other words, you can try radical 10 times radical 3, but that's not going to get you anywhere. So this time we just have to leave it the way it is. So when it says simplify radical 30, your correct answer is radical 30. All right, how about this? Let's look at 42. Oh no. Same thing. So radical 42 can't be simplified. Now, these are a little different because you've got a coefficient being multiplied by a square root. So radical 20, we saw a little while ago, could be rewritten as radical 4 times 5. So you've actually got here 10 times 2 radical 5. You multiply these together, and that's our final answer. Now, if you're not sure if you've done this correctly, one thing you could actually do is enter those both into your calculator, and you'll see you're getting the same number. It's a very long, messy decimal, but it is the same number. All right, what about this one? So therefore, okay, that's your final answer. Does that work? Yes. Now, how about this one? Radical 700. Well, this one jumps right out at you. Clearly, the perfect square in here is 100. And that's it. We're done. Now we have 2 radical 162. Let's see. This one's a little tricky. Let's look at the factors of 162. Ah, so we got lucky here. Look at this. We've got 2 radical 81 times 2. 18 radical 2. Okay. Right. Now, these are a little different because we're performing algebra directly on the radicals, but even then, at the end, when we have a result, there may be an opportunity to simplify it further, but not necessarily, right? So we'll check them all out. So this one, now you see how the way it's written, 2 is a prime number, 10 is not a perfect square, so you might think we're stuck. But if you combine these, you realize right away that, oh, look what we can do. We can rewrite it in a more convenient form. And I think you'll agree that this is a lot neater than this. And something like that will happen with number 18 if you multiply them out. Now, 6, not a perfect square, 15, not a perfect square. But when we combine these, um, and that again is a nice simplification. Now, 18, yeah, see again, 18, 15, no perfect squares here. So if we multiply 18 times 15, that's 270. Now, even now, there's no guarantee this will work, but we do know at least that this is equal to uh, let's try that. Now, remember earlier we showed that 30 can't be simplified any further. We actually remember that one from up here. Because if you look at those factors, none of them are perfect squares. So we're actually done here. Wow. So that does happen sometimes. Now, sometimes we also get lucky. Look at this one. So we already have a perfect square. Now, of course, you don't leave it as radical 5, 5. It just isn't done. You always have the integer first and then the square root. Great. Now, what's going on with these? We're multiplying two expressions. So remember, the way this works is we're multiplying the coefficients first, and then the radicals. So you're just rearranging it because you know that based on the commutative property of multiplication, the order in which we write these does not make any difference. Now, 48 has factors of, here we go. Let's choose that one. And we're good. Okay. Now let's, ooh, man, there's so many of these. We need the practice. All right, so let's multiply these together. Now, again, you can see what we're going to do. Clearly, 3 and 25 are factors of 75. And we ultimately end up with 60 radical 3. Oh, hold on. Now, with these, if you remember, so here we can rewrite this as radical 60 over 2. Now, we already know that this can't be simplified any further, so this is our final result. But I think you'll agree that it's simpler than radical 60 over radical 2. So even though we can't go any further, we've definitely accomplished something important here. Okay. Now this one reduces to radical 7. 7 is a prime number, therefore we have to stop. Now this one's different though, because when you reduce this one, 8, the factors of 8 are 1 and 8 and 2 and 4. So let's rewrite this as radical 4 times 2. Now we're done. This one reduces to radical 5, which of course 5 is a prime number, so we're going to stop here. All right, so now the next batch involves something a little bit different, addition and subtraction. Okay. These are a little bit trickier because we have to be very careful about what we can and cannot add and subtract. All right. Oh, and so once again, just a quick reminder, if you missed something, I'm going to be posting all these solutions on Brightspace later on. Now here's where we have to be careful though. One of the negative things I've noticed about PDF is that for some reason, if I try to PDF this document, it has a tendency to not pick up on the handwriting. So I'll be posting this in Word directly. So I'm hoping that you can read it on your Mac. I think you will, but if you're having issues, just let me know. I'm not sure what we can do about it, but this has been my experience with PDF. It doesn't seem to recognize the handwriting. So, but on the other hand, the Mac usually does. For some reason, it is compatible. I think that's because this tablet is meant for both Macs and PCs. So you should be okay, no matter which one you're using. All right, now we're going to combine. Now, remember the way this works is that you can add two radicals as long as they're the same radical. Okay, so here we can do this as just like it's like anything else. It's like if you had 3x and 10x, you would, or sorry, 2x. Let me write this down here somewhere. Okay. So you can combine them because it's the same object, x. But if it was 2x plus 10y, then there's nothing you can do with it. And the same thing holds with radicals. They have to be the same radical to add or subtract. Now, having said that, sometimes you can rearrange your radical into a more convenient form, but not always. All right, now this one clearly is going to give us 61 radical 11. So I'm combining 50 with 11. And since these are the same radical, we're good. And then down here, since again, they're both radical 3, I can rewrite this as -7 radical 3. Okay, so what you're actually doing here is 8 minus 15 radical 3. Okay. Now, this is what I was alluding to earlier. Look at this number 30. At first glance, you might say, we can't do anything because they're not the same radical. But it turns out that we can because there's a factor of 80 in 320. So what you really have here, without it being obvious, is 2 radical 80 minus radical 80, which is radical 80. But guess what? we know how to simplify radical 80. Now, if you wrote this on a test, I would not mark you wrong, but we are supposed to make it as simple as possible. So let's keep going. So ultimately, all of that ends up being 4 radical 5. Now, these two, again, we have the same problem, but if you notice, 5 is a factor of both 125 and 20. So if you take 125, oh, not 2. How about 3? Oh, bad luck. Okay. How about not 4, 5? Oh, yeah, there we go. So in other words, for doing something like this, we're trying to find if they have a common factor that can be reduced. So, and they sure do. Actually, let me write it. This. And then for the 20, uh, okay, so now we're in good shape because that means that this is equal to this. And now, of course, you can easily combine these into 7 radical 5. So at first, like I said, at first glance, you might have said, well, what are we going to do? They're different radicals. Oh, wait a minute. Maybe we can do something about that. All right, now can we do the same thing here? Well, let's find out. Let's take a look at 80. Now, of course, we've seen this before. Oh, well, that's right. It's this one. Oops. So in other words, we can just directly replace this. Now, this is radical 80. That means that 3 radical 80 is 3 times 4 radical 5, which is 12 radical 5. So we have to be careful with that. Don't forget about that 3 out there. So then ultimately we end up with 6 radical 5 minus 12 radical 5. And then we end up with negative 6 radical. All right. Well, that was interesting. Okay. Oh, what else do we have here? How about oh, I think we can maybe simplify these two. So by the way, if you notice right away the a factor which is a perfect square, you don't have to write the entire list. Like here, for example, okay, there we go. You don't have to go through the entire list because you can see after a while you get enough practice and you'll see right away that, oh yes, this is what we're aiming for. And then with 40, you can see that this is clearly going to be 4 times 10. So now don't forget though that one has a 13 being multiplied by it, and the other has a 5. So in other words, since radical 90 is 3 radical 10, that implies that 13 radical 90 39 radical 10. And then if radical 40 is 2 radical 10, then 5 radical 40 must be 5 times that. Okay. So we're done adding these together. The bottom line is 13 radical 90 plus 5 radical 40 is the same thing as saying 39 radical 10 plus 10 radical 10. And that ultimately leaves us with 49. All right. Now, the next batch, the last batch of problems is slightly different. We're engaging in a process called rationalizing the denominator. Now, what is this all about? Well, by convention, we try to avoid having irrational numbers in the denominator of any expression. So 1 over radical 5 normally is transformed into something a little different. Like if you remember from trigonometry, like you sometimes had results like radical 3 over 2 or things like that. You never had a radical 3 in the denominator or radical 2 because this process was applied to your results. So remember, you're always allowed to multiply a number by 1 without changing its value. So this is our strategy. So radical 5 is irrational because 5 is not a perfect square. We want to rationalize it. In other words, convert it to a rational number. Okay, in other words, we're making it neater, I guess you could think of it. So here's our strategy. Whatever the irrational number is, we multiply our expression by that number over itself. Okay, because radical 5 over radical 5 is just 1, and it's not going to change the value of our result. So we have in the numerator 1 times radical 5, in the denominator, radical 5 times itself. And so we've accomplished our goal of getting rid of the irrational number in the denominator. And again, if you type this into your calculator, 1 divided by radical 5 or radical 5 divided by 5, you'll see it's the exact same number. All right, so they're all done the same way. It's just that some of them, when you're done with this part, you can simplify it further. Some cases you can't, like this one. And if you can, you should always try to do so. All right, let's see what we can do with this one. Now, by the way, if you can reduce radical 8, you may want to take a shot at it, but it's not absolutely necessary because we're going to simplify anyway, if it's possible. So let's just do it this way. So you might think we're done, but if you recall from earlier, it's actually 2 radical 2. So in other words, we have the 3. Radical 8, as we've just shown, is equal to, 2 radical 2. So we have 6 radical 2 over 8. And now 6 over 8 is just 3 over 4. So remember, we always simplify whenever possible, no matter what the situation is. We never stop simplifying. In other words, we always look for every opportunity to simplify. So the original expression is equal to 3 radical 2 over 4. And that can't be reduced any further. Okay? And again, if you want to prove it, type them both in your calculator and you'll see it's the exact same number. Okay? Beautiful. So they're all going to be done the same way. Let's just get these other ones done here. And of course, 3/6 is 1/2. So we'll write it like that. And then we're done. Because 6 is not a perfect square. Oh, this one looks interesting. 10 over radical 20. Let's see what happens here. Now, this one can be simplified in 2 different ways. 10 over 20 is 1/2. But we're still not done because radical 20 equals radical 4 times 5. So that means I end up with just plain old radical 5. And I think you'll agree again, that's much simpler than this. So we're very pleased with our results. All right, what do we do with this one? Oh my God, what a mess we have here. All right, so let's rewrite it like this. The 28 can't be reduced. Well, actually, yes, it can. But I'll tell you what, let's do this first. Now, what we can do now, 3 times 28 is 84. What are the factors of 84? Yes, it's divisible by 3, by the way. You can tell because 8 plus 4 is 12. So 84 over 3 is 28. Well, that's interesting. Let's see, but we're looking for a perfect square in here if we can find one. Let's see, 6, 7, 8. Oh, okay. You know what? There isn't a perfect square, but actually, yes, there is. I'm sorry. This is the one we're aiming at. That's good. Oh, whoops. I'm sorry. The denominator is not radical 28, it's 28. And of course, 2 over 28 is 1 over 14. So this is as far as we can take it. Okay, I think there's a couple more of these, but they're very simple. So what about this one? What are we supposed to do with it? Well, let's do this. Guess what? They're both perfect squares. So this one is very easy. This is the same thing as 1/3. All right, and then this last one, so we're going to take this one and rationalize it. And since 6 can't be reduced any further, it's not a perfect square. It doesn't have any perfect square factors. We're done here. Wow, that was a lot of work. But by now you're actually pretty good with these concepts. You're experts in these concepts, as a matter of fact. Good. All right, that's what we like to hear. Experts, I tell you. All right. So now what's next is we're done with the reviewing. So what we still haven't done here is we were kind of towards the end of chapter 6, if I remember correctly. You don't need this. Yeah, where this is what comes next. I'm not sure if we're going to get to that today. Here we go. Chapter 6. So if I remember correctly, what we were doing, we introduced binomial expressions. And just a quick reminder, a binomial expression has two terms, but the restrictions here are that the exponent has to be a whole number, meaning if you remember that the whole numbers are these, the natural numbers plus the zero. And so you can see that these work because, for example, a constant like this is actually 2 times x to the 0, and 0 is certainly a whole number. And so x, something like this, is 3x to the first. That one, of course, is a whole number. So these do qualify as binomial expressions. Now, here we have ones that are not for various reasons. For example, here, remember 1 over x is x to the negative 1. So this one is the same thing as 3x to the minus 1 minus 9. Not a whole number, not a whole number, not a whole number. And here we have only one term. So those are all disqualified. They're not binomial expressions. And then we reviewed the FOIL technique, which enables us to multiply 2 of them together. Okay. We've done these a few times. So let's just quickly run through one more of these to get some practice. X minus 3 times x plus 4 looks like this. These two terms are first terms. Your product is x squared. Here's the outer terms. These are the inner terms. And these two are the last terms. That's negative 12. These can be consolidated. And that's our final result. Okay. And then I think we may have done factoring last time. But now, by the way, in this section, what we're trying to do is find the solutions of a quadratic equation. So you may recall that all quadratic equations can be illustrated as a parabola. Okay. So if you have something like this, we know that this is going to be a parabola. It'll take one of two forms. Either it's facing up like this one. And by the way, this depends on the sign of that coefficient of x squared. If it's positive, the parabola faces up. If it's negative, the parabola faces down. So as far as solving for this equation, what we're actually looking for is the points where it crosses this axis. Okay, so those are the 2 points that we're seeking to find the solutions. And for many applications, this is something we'll do very frequently, finding the solutions of equations, in particular quadratic equations. So there's two ways of approaching this. One of them is to find the factors, where basically what you're doing is you're taking the quadratic equation and breaking it up into a product of two binomial terms. So the one we just did, remember we have x squared plus x minus 12. If we multiply these together, we just got through showing with FOIL that x, oh, sorry, got it backwards. X minus 3 and x plus 4. So then in that case, x plus minus 3 and x plus 4 are the factors of x squared minus plus x minus 12, in the same way that 2 and 12 are factors of 24, because their product gives us back the 24. So in order to solve for x squared plus x minus 12, you could break it down into the two factors and set them equal to 0. And what ends up happening is that these are my two solutions. So if this graph is x squared plus x minus 12, the solutions are -4 and 3. And you can double check that by simply plugging those two x's into the original equation, and you'll see that in both cases you wind up with a 0. Now, the tricky part there is to actually find the factors. I find that factoring is a very, let's say, difficult procedure compared to our other alternative, which is the quadratic formula. So I'm pretty sure last week we did factoring. So what I'd like to do is jump ahead here and revisit our old friend, the quadratic formula, which you've seen this before. You recognize this, you know it very well. So remember, for the standard form, ax squared plus bx plus c, the solutions come from this formula. And because there's a plus and minus here, that means there'll be two solutions. Okay. So this one, I think, is much more straightforward than factoring. And what's good about this is that factoring is only straightforward when the a is equal to 1. For any other value, factoring can be an unbelievable nightmare. So this one will work every time. It works. It's the same amount of work, no matter how messy the equation is. So I think what we would like to do is every time we encounter a quadratic equation, we'll solve for it using the quadratic formula, because we're comfortable with it, but because it's quick and easy, you just have to be a little careful with it. Okay. So, all right. Anyway, so I'll tell you what, it's 9:45. Why don't we save this for after the break? We'll come back, let's say a quarter after. I'm going to pause the recording here, by the way, so there's not a half an hour of blank space. That would be very boring to watch. And in about a half an hour, we'll come back here. hopefully with plenty of caffeine in our system. And we're going to go through some examples of the quadratic formula, and you'll see that it's very straightforward. If you haven't done it in a while, with a little practice, you'll see that it's not too bad. And then, believe it or not, I think we'll be ready for chapter 8. Oh my God. So we're really zooming along here. All right, so I'll see you in about half an hour. All right, so let's get back to this. So here's the quadratic equation, a formula rather. So how do we do this? So we have x squared minus 3x minus 4 equals 0. Okay, so what we'd like to do is find the solutions without factoring it. Okay. We know we can factor it, but I think you'll agree that it's probably quicker and easier to just use the quadratic formula. So on the test, it won't actually ever, well, no, there are some questions where you're asked to factor, but most of the time you'll be able to do whichever technique you're interested in. So we'll have x squared minus 3x minus 4 equals 0. Okay, so in other words, we're trying to find, again, the 2 points where this parabola crosses the horizontal axis and remember, because of the way a quadratic function is written, that means that in this case, a is 1. There's an applied coefficient of 1 here. B is -3. And then C is -4. Okay. So now we need to plug these into the formula. Right. So let's do that. And you'll see so just let me just copy these from the previous page. A equals 1. B is -3 and C is negative. So when you make the substitutions, you'll have minus -3 plus or minus the square root of -3 squared minus 4, 1, -4. Or 2 times 1. Now, here's where you have to watch it. There's so many negatives floating around here. This is where mistakes are often made. Just be careful with the negatives. So you'll end up here with +3 plus or minus the square root of 9 plus 16 over 2. Now, we got lucky here because, of course, 25 is a perfect square. So we end up with 3 minus 5 over 2, 3 plus 5 over 2, minus 2, minus 2 over 2. And 8 over 2, which means you've got solutions of -1 and +4. Okay. And that's how we do it. Now, that means that if you draw this graph, and by the way, it's here too. If you draw this graph, what this indicates is that again, the original equation was x squared minus 3x minus 4. 2 points at which it crosses the horizontal axis are -1 and +4. So those are my solutions. In other words, it's not the zeros, but the -1 and 4 are my solutions. All right, or which is equivalent to saying that if I plug in -1 into the original function, I'll get 0. And if I plug in 4, I'll also get 0. Okay, so for a lot of applications, we'll need to actually solve for equations just like this. We'll set it equal to 0 and we'll solve for the respective variable values of x. All right, so there's one more here. And x squared minus 6x plus 8. Let's try that one. So you can see a equals 1. Again, there's an implied 1 here. B is -6, C is 8. So if you plug these in, this is what you'll end up with. Okay, and so remember, this is now positive 6. In the underneath the square root sign, we have 36 minus 32, which is 4. The square root of 4 is 2. So again, we're going to have two integers. We have 6 minus 2 and 6 plus 2 over 2, which reduces very nicely to 2 and 4. So that means in this case, when you draw the parabola, you'll see that both solutions are positive. So you end up with something like this. Okay. All right. Now this last one is a physical example of a carpenter building a table. It's a picnic table, which means it's a rectangle. It looks something like this. So let's say we'll let the width be X. The length must be 2 feet more than the width. So the area is the length times the width, or X plus 2 times 2, or times X rather. And so this is X squared plus 2X. And remember, it has to be 35 feet. 35 square feet, that is. So we can rewrite this in the more formal, let's say, hold on. Since we know that X squared plus 2X equals 35, we want to rewrite this in the standard form, which means X squared plus 2X minus 35 equals 0. So we're going to solve using the quadratic equation. And that is being done, let's see, right here. This is our formula. These are the substitutions. Now, here's an interesting twist, though. If you notice, if you do all the calculations, you end up with two solutions, -7 and +5, which is fine. But since this is a physical problem involving area, you can't actually have a negative length or width to a table. So that means that there's only one solution here, and that's the 5. Okay, so if you go back to your table here, and then the length, X plus 2, is therefore 7, and the area is, of course, 35 square feet, as we expected. All right, so that's it for 6. And that, like I said, that means that we're getting closer to our exam, which, according to my records here, should be on March the 5th, which is three weeks from today. And we'll allow the entire class for the test, because it's hard to predict how long any one person will need for it. So these annotated slides I will put in Brightspace as soon as we're done. And so now we have a little time. So I'd like to at least start chapter 8, which is what comes next. Now, I did mention before, 8 is a very, very different chapter than 5 and 6. 5 and 6 are an intensive review of algebra. Here we're introducing some very important real world concepts under the category of consumer math. So really the bulk of this involves interest rates. In fact, almost all of the content here has something to do with interest rates. So these are the kinds of things that you ideally would like to know about before you head out into the real world and you start finding yourself taking out, let's say, car loans or buying a house or possibly getting a credit card or something like that. So we're going to introduce or explain how interest rates are calculated. And so we'll start out by introducing the concept of what's called simple interest. Now, there's some key terms that we need to know here. Let me just quickly mention a couple of them. So let's say if a consumer borrows or lends money, the amount of money is known as the principal. In other words, if, for example, if a consumer deposits $10,000 in a bank, this is the principal. So the word principal will refer to the $10,000 that we put in the bank. If a consumer borrows $25,000 to buy a car, this is also known as the principal. So the word principal means there's an amount of money that we are either saving or investing or possibly borrowing. Okay, so it can go either way. It refers to borrowing and lending. Then you probably are aware that when you borrow money, you have to pay it back, of course, but you also have to pay it back with interest. Okay, so interest is paid to savers in let's say in a bank account. Let's say consumers who have invested money in a bank account, let's say, are earning interest on their principal. Now you're probably asking yourself, well, how can the bank afford to give me interest on my principal? Why are they letting me put my money there and paying me interest in the meantime? Because here's what's happening. The bank makes its profits by lending the balances in its customers' savings accounts or other accounts to other customers and charging them a higher rate of interest than they are paying to the savers. All right, so they're taking your money, they're paying you some amount of interest, let's say it's 3%. And then when somebody walks in the door and says, I need to borrow money to buy a car, the bank will lend your money to them, but they'll charge them, let's say 8%. Okay, so that's where the money's coming from for the most part. So this is how banking works. The bank is acting as a borrower and a lender at the same time. So, for example, a bank may pay 3% interest to its customers who have savings accounts and charge 8%, or let's say car loans. Okay, so the difference between those two rates of interest is how they're earning their profits. Now, they have money coming in from other sources too, of course. They have fees, for example. Like if you have a credit card, you may have noticed that if you pay late one month, they charge you a fee. That's very profitable to the bank, by the way. In fact, some banks, it's gotten to the point where some banks, they're earning more money from fees than from borrowing and lending. But here we're seeing that there's a spread between the interest rate that's being paid to the savers and or who are the lenders, by the way, and then the borrowers who are buying, let's say, cars or houses. And by the way, you may have noticed if you do have a credit card that you're not paying 8% interest, are you? The bank may also lend money to customers who have credit cards. So in other words, when you charge something on your credit card, you're basically borrowing money from the bank that issued it. So you go into the store and you buy $100 for the groceries and use your credit card. You're saying to the bank, please lend me $100 to pay for these groceries and I will pay it back to you with interest. Okay. So but here it's being lent out at a much higher rate of interest, often more than 20%. Okay. So it makes you wonder, like, well, how come I can borrow money for a car for 8%, but I have to pay 20% for my credit card? What's the difference between the two situations? Well, here's what we have to think about. keep in mind that when the bank lends money to somebody, hold on a second. When the bank lends money to customers, it is taking on a great deal of risk since the customers may not repay their loans. Okay, in other words, how do they know you're going to pay the money back? Just because you borrowed it doesn't mean you're going to pay it back. So this type of risk is known as credit risk. So the interest rates charged by the bank reflect this credit risk. So the amount that they charge you depends on many factors, but one of the most important ones is how much risk are they taking on? So let's look at the case of the car loans and the credit cards. So car loans involve less risk to the bank than credit cards. Why is this? This is because if a customer doesn't make his or her car payments on time, the bank can repossess the car. Okay, in other words, there's that always going on behind the scenes. If you miss a couple of payments, they can literally come to your house and take your car away because it technically belongs to them until you repay the loan. So the car acts, and by the way, once they take it back, they sell it to somebody else. So that way they recover as much money as possible from somebody who does not make the payment. So the car acts as a form of collateral. That's an important word. Collateral is real property that is used to guarantee performance of a loan. So with a credit car, the bank doesn't have that much risk. Yes, there's some risk. They don't want to be dealing with buying and selling cars that they've repossessed. They don't want to be bothered with that. But it's there if it's necessary. So somebody really truly doesn't make the payments. At some point, they'll just come and take it back. I don't know what you would have to do to get to that point. You'd probably have to miss several payments in a row. For them to actually do that, but it will eventually happen. Now, that means that when you look at credit cards, we have a very different scenario. With a credit card, there is no collateral for the bank. Okay, so in other words, for example, if a customer uses his credit card to go on an expensive vacation and is unable to make the credit card payments, there is nothing the bank to repossess. So therefore, the credit risk is much greater. This is why the rate of interest charged for a credit card is so much greater than for a car loan. The lack of collateral. So like I said, the interest rate they're charging depends to a large degree on credit risk. Now, you may not be aware of this, but everybody has, as individuals, we have different levels of credit risk. And you'll learn about this later on when you finally get your first credit card, you graduate. Individuals can have greatly different levels of credit risk. Okay, so individuals with high incomes and good repayment records will have good credit, and individuals with lower incomes and bad repayment records will have lower credit rating, will have not necessarily bad credit, but um, a lower credit rating. Now, how does that affect your um, experience in the market? So, in other words, imagine somebody who always pays their bills on time and they have a very nice income. They're going to be very safe. The bank will see them as very safe, a very low risk. The bank will be happy to lend them money, even if it's a credit card, and charge them a relatively low rate of interest. Okay. But a person who frequently misses their credit card payments or doesn't pay back loans and that type of thing, and in addition to that, maybe has a low income, they're going to be terribly risky from the perspective of the bank. So somebody like that, either they won't get a card at all if they ask for one, or else they'll pay a much higher rate of interest. So this part of it is very important because um, individuals can have very, very different credit ratings, and that means that they'll pay different amounts of interest for their loans. Now, if you're wondering about this, there are organizations that provide credit ratings to individuals, based on all these factors. They're one of them, Experian, TransUnion, and what's the third one? Equifax. Now, you might say, well, how are they finding out about my credit history? Well, because the banks make this information available to these credit rating agencies. Um, it's not it's not the case that they can't find out. Let's just put it that way. In other words, if you pay your credit cards on time every month, if you repay your bank loans, et cetera, that information is available to these credit rating agencies, and they will give you a great credit rating. They'll say, nice job, you have a really good credit rating. And the banks will see this when they decide if you can borrow money from them and how much interest to pay. If, on the other hand, you've had a pretty rough time of it, they will know these credit rating agencies will give you a very low credit rating, and that will cause you to either not be able to get credit at all, or else you'll have to pay a very high rate of interest for it. So all this information is out there floating around. It's available to these organizations because it helps financial institutions have access to these ratings. They don't want to do this themselves. It's a lot of work. So they, in effect, are saying, here's our information. You tell us how creditworthy these customers are. Okay. So the moral of this story, by the way, is always pay your bills on time. Okay. Otherwise, otherwise you'll find it hard to get credit when you graduate. So anyway, with the banks, though, the amount of interest they charge for borrowers is going to depend on the credit rating, and the amount they pay you for your savings account will depend on the level of interest rates in the economy. Okay, so right now, interest rates in the US are relatively low by historical standards. So the interest rates they're paying you are fairly low too. But if interest rates in the economy start to rise, you'll see higher interest rates being paid on, let's say, savings accounts or checking accounts. But that also means higher interest rates for loans like car loans and um, credit cards. Anyway, with all that background, we're going to start by introducing a concept called simple interest. So what's happening with simple interest? Simple interest, just here we go. Simple interest is interest paid on the principal of the loan. All right. So just as a quick, simple example, if let's say if a saver or a customer puts $10,000 in a bank account and earns a 5% rate of interest at the end of the year, the interest payment will be 5% of $10,000, which is calculated as 0.05 times 10,000, which is $500. Okay. So that is known as simple interest because it's entirely based on the amount of money you started out with or your principal, right? So now that raises an interesting question. Well, what other kind of interest is there? Good question. I'll just briefly mention this because we'll get to this later on in the chapter, but the other type of interest is known as compound interest. This is based on both the original principal. Actually, no, I shouldn't say that. This is based on previously earned interest in a bank account. So in other words, if you left your money in the bank for a long time, it starts to grow. And so like here, for example, at the end of the first year, I've got $10,500. The following year, I'll earn interest on both the original $10,000, my principal, and this $500. So this is where the compound interest comes in. The simple interest is simply 5% of 10,000. Compound interest is interest earned on any previously earned interest like this one. Okay, so that way, every year your balance goes up by more than $500. Okay, and we're going to see a lot of numerical examples of how that works. So, by the way, this is one good way to save for your retirement by keeping your money in the bank for a very long time. Okay, decades actually, and it will grow very, very quickly because you're not only getting interest on your principal or simple interest, but you're getting interest on your interest, which is called compound interest. Okay, well now, let's introduce some variables. We're going to use these variables in the equations of this chapter. So P is the principal. That's the amount of money you either borrowed or lent with the bank or whatever source it happened to be. Now, R is the rate of interest. It's a percentage, but it's usually expressed as a decimal. For example, what we were seeing earlier, if a bank offers a 3% rate of interest on a savings account, then R equals 0.03. Okay, because remember, 0.03 equals 3%. In the formulas we're about to use, we'll always use decimals rather than whole numbers. So in other words, you would not type 3% into your calculator, you would type 0.03. All right, so just be aware of that. We're always going to use decimals. Okay, now what about these other variables? We have T, the time or the term over which I'm lending or borrowing my money. Okay, that'll have a huge impact on the amount of interest. If I borrow money for 1 year, I'll pay a lot less interest than if I borrow for, let's say, 10 years. So this is an important detail. And then A, now this A is kind of an important idea. I don't know why they chose the letter A, but A refers to a concept called future value. So for example, remember in the beginning, if a saver deposits $10,000 in a bank account for 1 year and is credited with $500 worth of interest at the end of the year, we say that the future value of the principal $10,000 is 10,500. Okay. So in other words, we started with 10, we ended up with 10,500. So we say that the 10,500, which we end up with, is the future value of the original $10,000. So the name tells you exactly what it stands for. How much do we have now? How much will that be worth in the future? That's what we mean by future value. Okay. So in many of these problems, that's exactly what we're interested in. So like imagine you're saving for retirement or just to buy a new car. it's important to know how much you'll have in the future based on how much interest you're earning now. And so that's when we'll use a formula like this. Okay. And then we also have capital I. Now you notice this is interest as well. What's going on here? So the distinction between these two variables is this. So in other words, remember from before, R is the rate of interest. This is expressed as a percentage or a decimal. And then capital I is the interest. This is the dollar value of the interest. All right. So once again, let's refer to that example we had earlier, where we started with $10,000, deposits $10,000 in a bank for 1 year with an interest rate of 5%. At the end of the year, the investor is credited with how much interest? Well, we're going to multiply the interest rate as a decimal times the 10,000. Okay, so using the terminology here, R, the rate of interest, is written as 0.05. Capital I, the dollar value of the interest, is the $500. So that's the distinction between these two. R is the rate, I is the dollar amount. Okay. So we have to be careful with this. The distinction between the two is one is a percentage or a decimal, the other is a dollar amount. So with all that being said, we can now finally define an equation. All right, we like equations. So simple interest is calculated in the following way. We take the original principal, we multiply it by the rate of interest, and then we multiply that in turn by the time for which we keep our money in the bank. Okay. So I equals PRT. Now we're going to see this formula quite often. I equals PRT. Remember, I is the dollar amount of interest. P is the principal. R is the interest rate. And T is the time, which is measured in years, by the way. So if, for example, the money sits in the bank account for only 6 months, we'll let T equals 0.5, which represents half a year. Okay, so just be aware, T is measured in years or fractions of a year, as the case may be. So here's another very simple example. Let's say that this time we're putting $1,000 in a bank that pays 3% per year. At the end of the year, the bank will credit our account with I equals PRT, meaning 1,000, the original principal, times the 3% interest rate times a year, $30. That's it. That's all we have to know. Now, how much do we have in the bank at that time? Assuming we didn't touch any of it, we'd like to calculate the future value. Now, you can see for yourselves that it's going to be $1,030. It's just the sum of the principal and the interest that we earned. So we can write this in one of two equivalent ways. A equals P plus I. Okay, so remember, this is the future value. Principal, and this is my simple interest. But we also saw that I itself can be rewritten as PRT. So I can replace this I with PRT, and this is an equivalent way of expressing that. A equals P times 1 plus RT. They both give us the same result. All right, then. So let's see if we can find a simple example. Yeah, so in other words, in this case we just considered, where we earned a $30 interest payment at the end of the year, that implies a future value of either P plus I, 1,000 plus 30, which is 1,030. Or we could use the second equivalent formula, this one, and we solve directly for the future value, which is again 1030. Here we have 1 plus R times T. R is 3%, T is 1 year. Now, what if we put money in the bank for less than a year? How do we adjust the form? Well, we don't really have to do anything because that T is measured as a number of years. If we leave the money for less than a year, T will be a fraction. Let's take a look at this one. An investor deposits $1,000 for 6 months, which is half a year, in a bank account that pays an interest rate of 4% per year. How much or interest do we earn? Okay, let's go back to this formula. I equals PRT, 1,000 times 0.04, 4% per year. But here, this is half a year. And so if you'd kept the money for a full year, we would have made it $40 worth of interest. But because it's only 6 months, we end up with 20. And then, of course, we can, if we need to, we can calculate the future value in 6 months. Of course, it's 1020. So that's how much we'll have in 6 months. So we know the future value is 1020. The interest is 20. The original principal is 1,000. So they have to add up to the same thing. All right. So if we want to calculate the future value of a sum that we've deposited, let's say in a bank, this is how it's done. Now, what's interesting about this formula is that it's actually a lot more flexible than you might think. Okay, let's take a look for a second. Oh, sorry, that's not the right formula. I equals PRT. Now, in many cases, we do want to know how much interest we're earning with a specific amount of principal, and we know typically what the rate of interest is that the bank's offering and how long we're planning on keeping the money there. But sometimes we want to solve for the other variables too. For example, what if I want to save and have a certain amount of money in the future? I need to know how much to deposit today. That is my P. So this formula can be rearranged to solve for P, R, or T. Oh, that's interesting. So, for example, you may want to know how much interest you may need to earn to reach a certain goal, or you may just simply need to know how long you need to leave the money in the bank, again, to reach a certain goal. So how would you do that? Well, it's just a matter of simple algebra. Okay. So like if we start here, I'm going to divide both sides by RT. Oh my God, because you can see these cancel each other out. That's all there is to it. To solve for R, I'll do something similar. I equals PRT, divide out PT, drop out. Oh, wait, sorry. Hold on a second. I did something wrong. Let's see. There we go. R equals I over PT. Okay. So if I need to solve for the interest rate, I just need the principal over the the interest over the principal times the time. And then I can also solve for T. So notice you're dividing out the variables you're not interested in. All right, so for example, okay, so we've got three new formulas all of a sudden. You can calculate the interest very easily, and algebraically, we can solve for P, R, and T. In each case, you're taking the interest rate and dividing by the remaining two variables. In this case, it's RT. Down here, it's PT. And down here, it is PR. So now here is an example of that. A homeowner has borrowed from a bank to finance various repairs. The simple interest is $20,000. The rate is 4%. And the principal will be repaid in 5 years. How much did they borrow? Which means, what was the original principal? Okay, so we've already seen, well, that's just this. P equals I over RT. So remember, the interest was 20,000. R is 0.04. 5 is the T. Now, here's where we have to watch it. If you're going to do this on your calculator, you're going to need to use parentheses for the denominator. Otherwise, you'll get it wrong. Okay. So if you have your phone right there, let's try this. 20,000 divided by the parentheses 0.04 times 5. 100,000. So that means that in order for me to have paid 20,000 in simple interest over 5 years with a 4% rate of interest, I must have borrowed $100,000 in the first place. That is my principal. All right. Now, how about this one? What if we need to solve for the rate of interest? Okay, great. So an investor puts $1 million into a CD. Now, let me just stop right there. A CD, certificate of deposit, is a special type of savings account where the investor must leave funds in the account for a specified length of time. For example, let's say 1 year, 2 years, 5 years, etc. So why would you ever agree to something like that? Because this type of account pays more interest than a traditional savings account. where the money can be withdrawn anytime. So as with a savings account, you can get your money back anytime you need it. But if you're pretty sure you won't need it anytime soon, you can get a little extra interest by putting it in a CD for a couple of years, let's say. And in the meantime, you can earn more interest, but you got to watch it. If you need the money back, they'll give it to you, but they're going to give you the penalties will be so high that you'll end up losing money. Now, sometimes there are exceptions, like they'll let you have it back if it's a true emergency, like you need to pay medical bills or something. But basically, you can count on losing all your interest and then some if you take your money back too soon. So you don't do this unless you're really sure that you won't need the money anytime soon, but it will give you more interest in the long run. A lot of people do this when they're saving for their retirement because they're looking, let's say, many years into the future. All right. So here we have that this person is putting $1 million into a CD for a year, and we're told that he's earning $20,000 with a simple interest. So the principal, is the $1 million. Simple interest is 20,000, and it's a 1-year CD. And we'd like to figure out what rate of interest he's earning based on those numbers. All right, so how do we do this? Well, we saw earlier that the formula for that is I over PT. So you can see what we've done, 20,000 in the numerator, in the denominator, 1 million times 1, and that reduces to 0.02, which remember, this is the same thing as 2%. Okay. Now, by the way, there's a button in here somewhere that'll help you with percentages if you're confused. I don't remember where it is. Oh, no, there it is. It's above the 9 on this calculator. So if I type, for example, 12, and I hit the percentage button, enter. If you hit 12, this button is directly above the 9, and you hit enter. First, it'll show in the window as 12%, but when you hit enter, or equals that rather, it comes back with the decimal equivalent, which is 0.12. I don't know if it can go the other direction, but it wants you to know that 12% and 0.12 are the same thing. So here, for example, 0.02 and 2% are the same thing. So with this information, we know that this individual must be paying a 2% rate, or actually in this case, earning a 2% interest rate on their CD. All right, now what about time? We still haven't solved for time. And once again, I would remind you that the word term in this context is the same thing as time. All right, so we can rearrange our original equation algebraically to solve for this. And let's see what happens. So this investor puts 100,000 in a CD. And the rate is 3%. And the simple interest is $30,000. How long will it be until the CD matures? In other words, how long is the money going to sit there? So we plug it in. Now remember, this formula is T equals I over PR. And so you can see that that means we must have left the money there for 10 years. On the calculator, you would do this. Now, by the way, I do want to point out too, I don't think every calculator is different. Some calculators do not like you to put it in commas. Let me just check that out of mine real fast. Actually, I don't think there are any commas on this keyboard. I guess that means no. So, but do not forget the parentheses. Yeah, so it does come up in 10 years. So this is something you really should practice with, although we'll get plenty of practice here. When we get to the chapter 8 problem set down the road, we'll definitely do quite a few of these. Okay, that's going to be a while, by the way, after the first midterm. So we're talking about late mid-March, let's say. But when we do get back to this point, you'll see that it's awfully important to be careful with those parentheses. Okay. So we've kind of exhausted the subject of simple interest, which remember is interest on principal only. The tricky one is the compound interest. Now you can see there's a terrifying looking formula here that we'll need when there's both simple and compound interest involved. And this one, we definitely need to get some practice with the calculators because there's a lot going on here. So let's take a look at this thing. Now, A, as we saw earlier, is the future value. How much will we have in the bank in the future? P is the principal. R is the rate of interest. T is the time. Now, here's something new. We have this new letter N. What is that all about? All right, well, that's an interesting question. N. So first, let me give you a chance to catch up with this, and then we'll explain what N means. Okay, so the way it works with the bank is this. Now, if you notice up to this point, so far, all the examples were based on the assumption that interest is paid once per year. In other words, the annual rate of interest is credited to an investor's account at the end of the year. This, by the way, is known as annual compound. The word compounding means how often is interest credited to your account. In practice, it normally isn't done this way. All right. So, what other methods could be used to credit interest to your account? Suppose instead that the bank credits 1/2 of the annual rate of interest to a customer's bank account every 6 months. All right. So in other words, for example, instead of paying 4% at the end of the year, the bank pays 2% every 6 months. This is known as semi-annual compounding because semi-annual means half of a year. Now, of course, if they can do that, what else can they do? How about this scenario? Suppose that the bank credits 1/4 of the annual rate of interest to a customer's bank account every 3 months. This is no, we can probably guess. So here, this means 1% every 3 months instead of 2% every 6 months. or 4% every year. This is known as orderly compounding. So that N in that formula that I just showed you tells me how many times per year interest is credited to our account. Okay, so N represents the compounding frequency, as it's called. How many times per year interest is credited to our account? Now, the standard numbers are these. Twice a year, N would be 2, semi-annual, that is. Quarterly, up here you can see it is N equals 4. Monthly would mean N equals 12, where you get 1/12 of the annual amount every month. And then daily would mean N is 365. Now you're probably asking yourself, what difference does this make? Good question. And which approach do banks actually use? Another good question. So as this is the, and we're going to prove this with some equations, as the compounding frequency increases, the compound interest increases, the simple interest remains unchanged. And the total interest that we earn or pay, and remember, just as a quick reminder, total interest equals the sum of simple interest plus compound interest. So even if the simple interest doesn't change, if the compound interest goes up, total interest increases as we increase that value of N. So when N goes up, simple interest stays the same, but compound interest goes up, so total interest goes up. Now that can be good or bad, depending whether you're the borrower or the lender. Okay, so in other words, as a lender or saver, the higher the compounding frequency, the more interest is earned. So you want to see a very high compounding frequency if you're lending or saving your money. As a borrower, though, the higher compounding frequency, the more interest is paid. And that means you don't want to see that. If you're the borrower, you do not want interest to be paid on a very frequent basis. Now, what about in the real world? How does this work? Well, in practice, banks compound interest on a daily basis. Okay, so there's when you look at your savings account, when you look at your credit card statement, they're compounding interest on a daily basis. This is the standard in the United States, at least. There might be some scenarios where it's different, but for just standard bank accounts, for credit cards, that type of thing, for car loans, most cases will be daily compounded. And the others will usually only show up in very specialized types of situations that, maybe like corporations enter into, but pretty much this is what we're going to expect. So, well, that's what that's all about. Now, once that's been established, what they're going to want us to do is get some practice with this. In other words, this horrifyingly scary looking formula is going to be used in these cases. So just as a quick aside here, When interest can be compounded more than once a year, we will use this formula to compute future values. All right, let's try that again. This one, yeah. There we go. So in other words, if there at least it's possible that we can have compounding that's more than once a year, we'll use this one. Only when we know for a fact that interest is only compounded once a year. So when n equals one, we can use simpler versions. A equals P plus I, which in turn means A equals P times one plus RT. Okay. Now, I do want to point out that if you use this formula when n equals one, you'll just end up with the same result anyway. But so here's the simple version once a year. This is for all the rest. Okay. Now, unfortunately, this is a fairly messy formula. So we absolutely need some practice with our calculators. Now, here's the example they want us to look at. An investor deposits $1,000 into a one-year CD where the rate of interest is 4%. How much will they have at the end of the year? In other words, what is A? Because that's the future value. If the interest is compounded, we're going to have four examples: annual, semi-annual, monthly, and daily. And so the whole point of this is not only to get some practice with the calculators, but to see how these compounding frequencies affect the results. Okay, it's kind of interesting to see how much of a difference it makes. It may not make quite as much difference as you think, but it's awfully important to understand how this works. So we're going to use, by the way, we're going to use the complicated formula for all four cases. So because we have $1,000, put it in the bank, P, the principal is 1,000. The annual rate of interest is 4%. Convert that into a decimal, and it's a one-year deposit. So we have these three values. The only thing that's missing is N, and that depends on whether we're in part A, B, C, or D. All right. So, for example, part A. So we're going to solve for this. So you can see it's a very simple case because we had so many ones all over the place here. So in this case, we very simply end up with $1,040. So we could have just as easily done this. God, what was that? It makes me nervous. It means I better save this file before something goes horribly wrong. So in this one case and one case only, we could have also used this very simple formula. Actually, I'm running out of space here. Hold on one second. Of course, it's the same thing. Now, in many of these cases, we may be asked to do something else. So let's just take a look at this for a second. So we know that in this case, A is 1040. And the principal is $1,000. That implies that the total interest we earned is A minus P, or 1,040 minus 1,000, which is 40. Of course, if we started with 1,000, we ended up with 40. We must have earned $40 worth of interest, but simple interest in this case is, as you know, I equals PRT. It's also $40. So since total interest is the sum of simple and compound interest, that means that 40 equals 40 plus 0. And so therefore, the compound interest in this example is 0. There isn't any. Okay. Wow. Now let's consider the second case where we have semi-annual compounding. And let's see what happens. Remember, P is 1,000, R is 4%, and T equals 1 year. So if you get this formula back, it is, go grab it. Oh, and yeah, n equals 2. What you've actually got here is 1,000 times 1. So you can do this directly in your calculator. You probably should consider doing it this way, going from right to left. Notice 1.02 squared, you should do first. And then equals. And then whatever number comes up in your screen, you multiply by 1,000 equals again. And you should have 1,000, oops, $1,040.40. Okay, now this is a huge deal. We'll have to do this again next time, by the way. We'll have to go back and revisit this entire discussion because it's very complicated, but at least now we have a sense of where we're going. I would like you to notice here that when n equals 1, A equals 1040. When n equals 2, A is 1040.40. Now, where did that extra 40 cents come from? This is the compound interest, which is the same thing as saying interest on interest. So in other words, we have total interest is $40.40. Simple interest doesn't change. The difference between the two is our compound interest. And that's that remaining 40 cents. Okay. So in other words, just by having semi-annual compounding, all of a sudden we've earned another 40 cents worth of interest, which doesn't sound like a lot, but if you kept the money in the bank long enough, this starts to really pile up after a while. So this is a huge deal. So then when you carry on with the remaining examples, you'll see that each time, although I think we may be out of time now, I just want to point out, and we'll revisit this next week, of course. We'll start and revisit all these wonderful ideas. What you'll notice is that as it increases, total interest will continue to increase. Simple interest remains unchanged, and compound interest increases. That's where the extra interest is coming from, by the way, from the word compound interest. That's in general how this works, okay? All right, so I see it's around 11:30. I think that's enough for now. So next week, who knows what's going to happen with the weather, but let's say we'll be back in person. What we're going to do is carry on with chapter 8, but first we have to remember to do the third and final part of chapter 5, those problem sets, plus the chapter 6 problem set. There's only one, but it's very long. That might swallow up the whole class. If not, we'll take a look at these examples again. So remember, right now, our main focus is on getting ready for the midterm, which is based on chapters 5 and 6. If we also have time to get a little more chapter 8 done, that's fine. But that's not our main goal right now. We need to be ready by the 5th of March for that first midterm. Okay. So we'll stop here. When we're done, I'll post these slides where all the handwritten notes are and the video. And then that way you can come back and review later on as you see fit. All right, so I guess that's it. We're done. So I'll see you all next time. Okay. All right, bye.
Thank you. Be safe.
All right, see you later.